I'm about to show you an Olympiad-level physics problem that looks simple, but it's my guarantee. You will get it wrong. Yes, definitely wrong. Don't believe me? Then watch this. The setup is simple. I have a tall candle, a short candle, and a glass jar. When I trap these candles under the jar, they will produce carbon dioxide. So, what happens next? Will the tall one die first? Will the short one? Will neither flame go out? Or will they both go out at the same instant? It's a classic counterintuitive problem that stumps almost everyone. Anyways, pause the video, lock in your final answer, and let me know your choice in the comments. I will wait. Done? All right. Now, if you chose option B, the short one, congratulations! You fell right into the trap. That's a perfectly logical answer, but it's completely wrong. But wait, if B is wrong, is the answer A? Or is there a trick, and the answer is C or D? Let's stop guessing and see the reality. So, we know one CO2 molecule is made of 1 carbon and 2 oxygen atoms, giving it a molar mass of about 44. On the other hand, air is mostly nitrogen, which has a molar mass of about 28. Even with overall 21% of oxygen and 1% of all other gases mixed in, the air in the atmosphere has an average molar mass of about 29, which is now also less than 44. Another important aspect to consider here is that density of a substance is directly proportional to its mass. And since the molar mass of carbon dioxide is more than that of air molecules, the density of carbon dioxide is greater than the density of air. Thus, by Archimedes' principle, CO2 molecules must sink downside in the jar and the air must float upward. Therefore, CO2 must snuff out the shorter candle first. So, your brain correctly concluded about option B, and under normal conditions, this would be 100% correct. But in this case, that's only half the story. You missed the hidden variable, the game changer that flips this entire problem on its head. That is heat. Yes, the flame produces CO2 gas that has a temperature of hundreds of degrees. And according to ideal gas law, when you heat a gas, its molecules gain a tremendous amount of kinetic energy, spreading out, occupying more volume, and becoming far less dense than they were before. That is, the volume of a gas is directly proportional to its temperature. And if you rearrange the equation to solve for density, you find that simultaneously, its density is inversely proportional to its temperature. So, due to high temperature and more kinetic energy, the CO2 molecules spread out and occupy more volume, resulting decrease in its density. So, instead of sinking, the superheated carbon dioxide and other exhaust gases rise. This creates a powerful, invisible, and natural engine inside the jar, a convection current, which is a continuous circular flow that transfers heat. And this convection current is acting like a conveyor belt that is delivering all the toxic oxygen-poor exhaust to the top of the jar. Since this exhaust, full of CO2, has nowhere to escape, it accumulates at the top of the jar, forming a toxic oxygen-poor layer that grows downwards. And since candles need oxygen to burn, the taller candle is the first to have its oxygen supply choked off and will die first. Whereas the shorter candle survives a little longer in the cooler, oxygen-rich air at the bottom. So, option A is the correct one. Anyways, this beautiful physics is not just present inside our tiny jar, but it is the same principle that lifts a massive hot air balloon to the clouds. It is why your AC is installed high to let cool air sink, and your heater is low to let warm air rise. And on an epic scale, it is the shocking reason in the Earth's mantle that moves the very continents we live on. The same physics from a candle flame to planet Earth. Now it's your turn to think like an engineer. If you wanted to keep both candles burning for the maximum possible time, and you could poke only one small hole in the jar, where would you poke? Near the top or near the bottom? And if you have a chance of poking maximum 2 small holes in the jar, then where would you? Think carefully about the convection current we just saw, and let me know your answer and your reasoning in the comments below. And don't forget to like and subscribe.